In this video, I want to introduce the idea of a depth-first search in a graph. We'll talk about what it is, sketch through how it works, and then see an example in code. To get us started, I want to be very clear about what a depth-first search, or a DFS, actually is. It's really not just a searching technique. It's more generally a traversal technique. It's a particular way for you to walk through a graph. Sometimes you can use this to search for a particular node or path, but sometimes you can use a DFS even when you're not searching for anything. So with a BFS, a breadth-first search, we've seen how to find the length of the shortest path. But sometimes you might want to actually generate full paths. For example, if we look at the graph that we can see on the screen, if we wanted to start at this 0 node and end up at the 5 node, if we wanted to return a valid path to get from the 0 node to the 5 node, one thing we could do is start a DFS from the 0 node and try to see what the path looks like to get to a 5 node. So generally, if you want to traverse an entire portion of a graph, a DFS is a way that you can do this. That's sort of one clue you can use to identify the pattern where you should use a DFS. Note that you can do this using a BFS as well. You can really pick whichever strategy you want in those scenarios. If you want to generate all paths in a graph, there are many different cases where you do that, but if you want to do that, a DFS is usually the way to go. A BFS doesn't make that much sense in that case. So if we wanted to, for example, represent that there is a path 0, 1, and another path 0, 2, 3, 5, and another path 0, 2, 4, that would be a pretty good situation to use a DFS to generate all of the relevant paths. So the way a depth-first search works is it goes deep into one direction first, instead of going level by level like a breadth-first search. With a BFS, a breadth first, usually you pick a particular node. Let's say we start at the 0 node. And you say, all right, as the first action, let's go ahead and explore all of my neighbors. So in this case, you're going to have the 1 node and the 2 node. And after you explore these nodes, you move on to whatever nodes come after that. You go this level, and then the next level, and then the next level, like this. The difference here with a DFS is that you don't look at all of the neighbors of the 0 node. Instead, you say, let me pick one neighbor. I'm going to pick this one right here, the 2 node. And then you say, let's go deep down this path and search as far in this direction as we can before we look at the 1 node on the left. So at the 2 node, you repeat the process. You say, let me pick one neighbor. Let's say we picked the 4 node here. And then at the 4 node, you could repeat the process and say, let me look at one of my neighbors, but I don't have any neighbors, so you stop. And that's how you finish DFSing in one direction. Then you finish going down the 4 path, you come back and say, all right, let's go down the 3 path, because that's another neighbor of the 2 node. And you focus in just on this 3 node. And then you kind of continue down to hit the 5 and so on. So a depth-first search is saying at every step, pick one of my neighbors and explore as far down that direction as you can before you go to any other neighbors. So you can notice that we're sort of repeating a process. We're saying at the current node, find one neighbor, search that path. Then at that node, find one neighbor, search the path. So you can imagine that recursion kind of makes sense with a DFS. And DFS certainly can be implemented recursively, and it very often or very frequently is implemented recursively. But it can also be implemented using a stack. And on Interview Ace, we're going to go ahead and focus on the implementation of a DFS using a stack, not the recursive implementation. The reason is because if you implement a DFS using a stack, it looks very, very similar to a BFS, a breadth-first search, which you're already familiar with. So this means you'll be able to pick it up much faster if you learn it with DFS with the stack technique, and you can really solidify these skills so that whether you have a BFS or a DFS, you can implement it confidently and quickly because you've practiced it so many times. So I want to go ahead and walk through what the DFS looks like with the stack, and I hope you'll be able to see that it is very, very, very similar to what you know in terms of BFS with a queue. So let's go ahead and create a stack here. Create a stack, which is just going to look like our queue. It's just going to be an array that contains some elements. The difference is that whenever we want to remove an element, we're going to do it from the right-hand side because it's a stack. So let's say we wanted to just, we start with the 0 node. That's what this S means here. It's our start node. And we just want to print this whole graph using a DFS technique. Well, the way we can do this is we're going to go ahead and just so we put 0 onto the queue, stack. That's the very first thing we do, right? Because we have to start with our start node. Then we can remove the 0 node, as we always do, and we want to process it. So we need to keep track of all of the neighbors of the 0 node so that we can handle them later. So we're going to add 1 and 2 onto our stack. If you remember, I explained that we should only be focusing on one neighbor, and that is still the case, but we are adding all of the neighbors to the stack so that we don't forget to process certain neighbors later. Okay, now we've finished with the 0 node. There's not that much we need to do on it, so we can go ahead and get rid of it. I'll just have this be our little section of things that we're not using, and I'll clear them up at the end. So now that we have added all of the neighbors of the 0 node onto our stack, we need to pick one. We want to pop off the stack. So in a stack, you can only access the top element, which is going to be the last one here. Oops. So we're going to pop off the 2. Let's remove it and process it further. So, you know what? Actually, if we're printing out these nodes, let's say we are. Down here, let's just keep track of what is printed. So we can do it like this. So the 0 is the first thing that is printed, because when we process the 0 node, let's say we had printed it. Now we go ahead and remove this 2 node so that we can process it. We say, all right, let's go ahead and print it as a part of processing it, and add all of its neighbors to the queue. Sorry, to the stack. Then you're going to add the 3 node because of this edge right here, and then the 4 node because of this edge right here. So you add 3 and 4. Now we're done. We want to go ahead and DFS deeper down this route. So we're going to say, all right, pop off the 4 and process it, which means we're going to print it. Oops. Let's move that into its position. So we have 0, 2, 4. And we need to add all the neighbors of 4 onto our stack. 4 doesn't have any neighbors, so we can actually just stop right there. Now we repeat the process. So we want to go ahead and pop off our 3 from the stack. Oops, we don't need all of that. We just want the 3. Remove it from the stack. And we want to process it. So we say, all right, print that next. And then we want to add all of its neighbors onto the queue. So the only neighbor that 3 has is 5. So we can insert this right here. We repeat the process. We say, all right, grab 5 off of the queue. Sorry, the stack. And you want to add it to our output down here. And then we want to add any neighbors of 5 onto the stack. Well, there are no neighbors of 5, so we can go ahead and stop. And now you can see what I mean. I'm going to pause for a second with the walkthrough. We are currently here. We just finished the 5 node. Now that we're done with this whole subsection of the graph, we have to go back and handle this 1. This is what I was referring to earlier about we don't want to forget the other neighbors we have to handle. So the reason we added this 1 node in the beginning is so that we would have it here. Now that we've finished this entire right portion of the graph, we remember that the 1 node needs to be processed because we put it in our stack. All right, so now we have this 1 node left. We are going to repeat our same process. We are going to remove it from the stack and add it to our output. One thing I want to be clear about is if there were more nodes over here, we would not have processed them until right now. Before this point, we would not have done anything to any nodes that are connected to the 1. In this case, there aren't any, so that's not really relevant here, but that's an important point, is that we were exclusively focused on this portion of the graph. Okay, so we've processed our 1 node. We say, does 1 have any neighbors? No, it doesn't. So we don't have to add anything. We try to repeat the process, but we realize we have an empty stack, and that's how we know we're done. So if we go ahead and walk through this ordering, if we try to figure out like what does this really mean in our graph, we start at the 0 node, and then we go to the 2 node, and then the 4 node. Oops. We go from 0 to 2, and then 2 to 4. So we went really deep down one path. That finished, so now we sort of backtrack from the 4 to the 2 node, and then we go really deep down this path. So we say, all right, we were at 4, now let's go to 3, and then to 5, and then you get stuck. So you backtrack, and you backtrack one more time to here. Lastly, you say, all right, go down this route to hit the 1. And that's the order of the depth first search we're executing. Now, it's not the case that this is the only way to do a DFS or the only output for a DFS. You could certainly do a DFS where you go down this route first and you would get a different order of the nodes, but it would still be a DFS. It doesn't particularly matter. But with a stack, usually, well, not usually, in all cases, you pop to remove a node from the stack, which means that you're going to take the last element that you add. So if you add 1 and then 2, you're going to pop off 2 first, because that's how a stack works. Okay, that covers how a stack works. I want to briefly go over the complexity. It's not very different from what we've seen before, but it's worth considering, or worth discussing. So let's go ahead and start by defining our variables. So v is going to be the number of vertices in our graph, which is going to be, in other words, the number of nodes in our graph. So here we have a total of 6 nodes. E is going to be the number of edges, so the number of connections between nodes or vertices. We can say that our time complexity is going to be O of v plus e, just like a BFS, and our space complexity is going to be O of v, again, just like a BFS. To be clear, I'm only describing the time complexity and space complexity of executing a DFS. Building the graph or any other things that you have to do in the problem might change this complexity, but the DFS itself should have this complexity. Let's start by focusing on the time complexity. The V is here because every node in our graph has to be added to the stack at some point in time, in the worst case scenario, right? Because if we're searching or traversing the whole graph, we have to process every node, which means it has to be added to the stack. And adding to the stack happens in constant time, so that's just order of the number of vertices, which is v. The reason we have the number of edges is because of that question I asked, which was, or not question, but when we would pull out a node, like let's say 3 here, we would say, all right, grab all of the neighbors of this node and add them to the stack. So we're going through all of the outgoing edges from the current node. If you go through all of the outgoing edges from every node in the graph, you're going through all of the edges in the graph. So that's why we have the E right there. It's not the case that at every iteration we go through every edge, but in total we do go through every edge. In terms of the space complexity, the worst case scenario is going to be order of the number of vertices. This you can see if we had some sort of graph that looked like this, because our stack would contain all of these nodes at one point in time. Because we would add this node, and then this node, and then this node, and we wouldn't have backtracked at all. We keep adding all of these without popping anything off. So we have however many vertices there are, that's how big the maximum length of our stack is at any point in time. That's all for the approach. Let's go ahead and switch over to the implementation. Now, let's see an example of how to execute a DFS in JavaScript. To get us started, I have an input graph that's the same one we saw in the approach. I've set up the boilerplate for our function, and I've written a small test here so that we can test it out when we're done. So we know we're going to want to create a stack because that's how we're going to execute our DFS. One thing that's nice here is you don't have to be that careful like you do with the BFS. If you remember, we used a Q class for our BFS because we didn't want to be shifting from the beginning of an array or removing an element from the beginning of an array because that takes linear time. With a stack, you're just popping off the end. So in JavaScript, you can actually pop off the end of an array in constant time. So we can just use the built-in arrays here. Now, this code is going to look very similar to what we know for a BFS. We're just going to say continue iterating as long as we have some sort of elements in our stack. Now we want to grab out a node from the stack. So it's going to say pop off the stack and store that in a node. Now we want to process the node. We'll come back to this part in a minute, as we usually do. Once we've finished processing a particular node, we want to say grab all of the neighbors of this node and put them onto the stack. So we want to say neighbors is going to be graph or at that node. And then you just want to say neighbors dot for each. So for each neighbor, what do we want to do? We want to say stack dot push that neighbor. So add that neighbor onto the stack. There is one thing, which is if you have like the for node, when you do graph, this graph here, at for, you get undefined. So we want to do a quick check here. This is just going to say if neighbors is undefined or is false, so you just go ahead and continue to the next iteration of our loop. You don't need to push anything onto the stack. This should be very familiar based on the DFS stuff. Now we want to figure out how do we process every single node. Well, the important thing here is we just want to print every node in the graph. So we can just say console.log that node, and that's really all we need to do. I realize we actually don't need to console log the output of this. We just need to invoke our function, because this function will be printing out for us. So we should be getting the output that we saw earlier. So let's go ahead and execute our code so that we can confirm this. So we'll use control backtick to open the terminal. Say run node intro.js, and nothing was printed. Why is that? Let's see. Oh yeah, we have nothing in our graph, or in our stack, sorry, so we'd never enter this while loop in the first place. Of course, we want to say stack.push our start node. And we should make sure the start node comes as an input here. And let's just say 0 is our start node because that's the example we saw. So now we can try this again. So we'll run node intro.js, and we see we get 0 to 4. So we're going down that one branch that we saw earlier. Then we backtrack a bit and say go down 3 and 5, which we saw. And then we backtrack all the way and hit this one node at the end. So it looks like that's working correctly. We can go through our complexity here. So we'll say v is the number of vertices in our graph, e is the number of edges. We know our time complexity is going to be O of v plus e, and our space complexity is O of v. In terms of the time, every node is going to be added to the stack in the worst case scenario at some point in time. So we need that v. We're going through right here all of the neighbors of any particular, actually here is when we're actually iterating through them, but we're going through all of the neighbors of a particular node, which is also the same as the number of edges that node has. And in total, or we're doing all of the edges for each node, and we're doing this for every node in the graph. So in total, we go through every edge that's present in the graph, so we need to have this dependence on E as well. In terms of the space complexity, the stack in the worst case scenario would have the entire graph sitting on it at one point in time if we had the graph that's just sort of like linear, like we saw in the approach. And in that case, we would have O of V as our space complexity, handling the worst case scenario. That's all for this video, and I'll see you in the next one.